And the list I came up with, and maybe everyone will look. We're going to begin our panel discussion, consisting of Silvano Colombano and Marc Cohen, Scott Howe, and Weinert Bierstadt, who all four gave papers, in the case of Scott, 2 papers this afternoon, around and about themes of robotics and mobile architectures. Habitats that might be robotically controlled before they're ever, from Earth or some remote station, before they're ever occupied by humans. And so some buzzwords that seem to fall out of everyone's talk, all or some, turned into a list of self-hyphenations. These papers tended to talk about structures that were self-replicating, self-tending, self-repairing, self-assembling, self-configuring, self-leveling, and self-transporting. So I can read that list, and perhaps the audience can think of a particular stimulating topic from that list, or perhaps the speakers can think of ways they might not have thought of or have already thought of to tie them all together. And that would be self-tending, self-replicating, self-repairing, self-assembling, self-configuring, self-leveling, and self-transporting. Why don't you start, Scott? Does that list ring any bells?
That's my list.
It's everybody's list.
So one of the critical things when we're talking about construction in harsh, extreme environments is the difficulty it is for to protect the person on the job, the person that's living in the environment, the person that's doing the work in the environment, and the difficulty, in other words, if there's a construction site, if a person has to don the suit, work with thick gloves and things like that, there's a lot of really difficult problems that make that give us a motive for putting automation into the picture. The automation that would not necessarily be necessary on Earth construction projects, but would make it much more viable in a very harsh, extreme environment. And I think that's one of the reasons that we use these terms, self-replicating, self-repairing, self-assembling, etc.
Yes,
what he said, but also I think that we need to distinguish between several levels at which we use these terms. I think that the simplest one is self-transporting, and then self-assembling in the sense of 2 or more units attaching to each other. Self-configuring, which suggests some degree of inborn intelligence deciding how it should be arranged, which in some respects may be actually the most difficult and profound. And then things like self-repairing, self-replicating, self-tending are kind of a middle group, or we group those together, and self-leveling is really pretty close to self-assembling. So I think we could structure this list into maybe three sets of terms, and look at each of the projects in terms of those subsets. The HATBOT project that I described really falls only into the self-transporting, self-leveling, self-assembling bit self-tending. It doesn't really do any self-replicating or self-repairing or self-configuring.
Yes, there is.
I think when you're looking to this kind of topics in space applications, then you have to be, as we now, sending all kind of Mars robotic systems to the Mars surface. In how far the robotic is a tool for this assembling modules for human being activity on the Mars surface, and how far this is supporting the human beings, and how far the human beings can interact with this self-assembling, and how what kind of technique the future will bring, as I shortly question the pneumatic muscles. What can we find in new techniques, as we found in DNA and nanotechnology, how the robotic system is functioning over there. And it means that a totally new field, but for further research and how to translate for space applications for the future.
Well, I'm glad I have a chance to talk again, because I think I really didn't make the major point I was trying to make in my talk. I'm trying at the same time to be very pragmatic and realistic. Okay, the pragmatic part comes from the fact that it's going to, unfortunately, it's going to be a long time before we really send humans to Mars, maybe back to the moon. Even further in time, if you're going to send it to the asteroid belt or something of this sort. So, what I'm asking myself, given the fact that we're going to send robots, no matter what, can we send robots that are, can we really improve the possibilities of robotic exploration to an extreme, where we can essentially rely on robotic sustainability, robotic ecology, something that really, I can send robots to the asteroid belt, and they're going to be there for 50 years and explore everything, and at the same time, as an extra bonus, get something ready for humans to go when they're ready. So when I talk about self-assembly and self-repair, I'm being very radical. I really mean robots that can do the whole thing. And the idea is that we're going to need that no matter what. And at the point when we're finally ready to send people, then it's going to be much easier, because we can have much of what people need is going to be there already. And but given the uncertainties of, I mean, can anybody guess when we're going to send people to the asteroid belt? To look at, could be 50 years, could be 500 years, who knows? But we're going to send robots there. I can guarantee you, within 100 years, we will have robots, checking out the asteroid belt. Maybe 50 years, I don't know.
The Japanese use the seas already on the way. They did the first asteroid sample return.
That's my point. Thank you. So, but the point is that if you want to do some mining, if you want to, so anyhow, that's the whole point. So at the same time, I come from a biology background. My thesis was on the origin of life and self-reproducing systems, artificial life. And so the idea is to use artificial life in a hardware context. Can we, in a sense, make robotic ecology, make robots in some sense alive, if you'll pardon me, push that technology, and at the same time, as an extra bonus, then make it easier for humans to step in when they can. That was the whole thrust of what I was trying to say earlier.
Any
Did you guys use any of the concept of what you learned from the space station? How we built that space station? I assume we still use a lot of the astronauts to do the construction of the space station.
Yes, in fact, I would say the single most important lesson we all learned is don't use the astronauts to construct it, use machines. And I worked on station for most of the 80s and into the early 90s, and I learned a lot of things about designing habitat modules and things like that, which I am applying, although there aren't any huge principles that I can point to. But mainly, you know, dealing with complexity by trying to have systems that are universally applicable, have a common module that truly is a common module, unlike what we have on station, where we're going to have 4 or 5 modules, each made on a completely different assembly line with different tooling and different detailing and different connectors, you know, and a system such as the one I described for the HAPOD or something like Scott's Mobitat, you would have to have a degree of commonality. You couldn't have one unit made by one country and another module made by another. They all have to be made on the same assembly line. There has to be a single integration contractor. But that doesn't mean to say that you couldn't contract out all the components, but you'd have all the life support systems made by country A, all the communication systems made by country B, and so on. And what you have to avoid is the kind of economic nationalism that prevailed during the space station program.
But your problem is harder when you try, because space station you just fly something up to the. Your problem if we want to land on Mars, that's another.
I'm only trying to land on the moon.
Oh, okay. That's still another big problem. The landing is pretty quite severe. The
Right.
shocks and the vibration.
You don't want very much of that. You don't want much shock and vibration.
But that's unavoidable.
If we can assume long-term mission scenario bootstrapping such that we get to the moon first and then to Mars, what are the necessary, in your mind, pieces of that set of events? And do we need, as Mark proposed, a separate ascent and landing vehicle for the moon? Do we need an orbital transfer vehicle? Do we need nuclear, solar, or power systems? What are the pieces that each of you might think go into the whole system?
As few as possible.
Okay.
That's really the answer. The number of different pieces, you want to keep it as few as possible. You want to optimize the pieces you have for their particular function, but you want to differentiate them to as few pieces as possible, different types as possible. Then the only way I believe you were going to see significant cost reductions is by simple economies of scale. That is to say, if you can manufacture 10 smaller modules and launch them on smaller conventional rockets, that's going to cost you a lot less in the long run and get the cost of spaceflight down more than if you have one huge module that you launch on one huge rocket that's one of a kind. And we can talk about all these different advanced launch technologies and reusable launch vehicles and expandable and extendable and blah, blah, blah. But we simply do not have a technology breakthrough that will really create significant cost reductions. The only thing we know that does that is economies of scale.
You should have lots of small pieces.
I wanted to comment on something like that. I think in architecture we have, it's kind of a concept called grammars, design grammars. Donna, you know this, but for the benefit of everybody, and or design semantics, where you have a series of like functions or like geometries, etc., can be described in the same way, or you can come up with, in effect, an alphabet or a language that describes the object being built. And I think really sophisticated design will go in and come up with a semantics or a language for the entire process, and break that down and find out what are the most, how far down can you reduce that? What are the primitives in that system? What are the primitives in that language? And then if we could produce a set of a kit of parts that represent these primitives, then they can be configured over and over again. That would be provide the minimum number of pieces that we're talking about, and those could be configured in different ways to create the various vehicles or the various habitats or the various functions that we're shooting after.
Since Scott and Silvano's papers were tending towards the theoretical, the ideal, the idea of self-configuration being a biggie on their list, and then Marc's and Mindart's papers were much more concrete and probably much more inflexible. How do we, as designers who know that we want all that flexibility and we want the ideal to go to the moon or Mars, so that the best is there is the first initial infrastructure, and yet reality probably dictates, as Marc pointed out, 25% of his project is devoted to shielding, probably putting some prefabricated element on the planet and covering it with regolith is going to be the initial base. And how can, that's one extreme, and then the ideal theoretical is the other. How can we bring these two closer together?
Well, first of all, may I suggest you have it exactly backwards, that Micah and I were in fact the most theoretical, in a sense, that we had the least practical. And Scott was showing designs for real hardware, and Silvano was showing real hardware. And you know, until you can reduce your concepts to practice at some level, it really is theoretical.
Then if it's all theory, anyway, do you see what I'm getting at? That the shielding, for example, could be the deal killer.
Does anybody see what she's getting at?
No.
I'll just try to. I have something there. I'm not sure it's going to come out or not. But first of all, I want to again second what Scott said about the idea of this construction grammar. The point is that on Earth we don't need that. You know, we have the flexibility of our brain, resources. We can do anything we want. We can throw it away after a year or whatever. So as we go into space, the cost and everything drives us to be much smarter about how we build. And so we need to have this new theoretical foundation for building. And I think both you and Marc are right. I mean, when you were saying, well, one is theoretical, one is practical, I agree totally. But then when he said it, I agreed with him too. Because yes, we have some beginning of hardware, so but there's going to be a long time before the snake bot can be turned into a happy bot, which can be turned into a real habitat. So, and in some way, starting from the other end, figuring out exactly what the habitat's going to be like is much more practical. Yet they haven't built it yet, so who knows?
He was dodging.
Anyhow, we need both, and we have to continue trying to go both ways and increase besides each other.
He was dodging my question for fear that I was going to take the legs off his module and bury it.
Well, actually, to answer your radiation question, I have a funded project where we're developing an advanced concept for radiation shielding called carbon-filled carbon, which we can apply to the outside of the module. And I'm supposed to have it delivered from the manufacturer they're supposed to ship on Friday. And then I'm sending it to Brookhaven National Lab where we're doing a particle accelerator test on that and other materials. Because the idea that you're going to bury everything you put on the moon under all this regolith may be fine for a city that's going to be permanent and fixed, but in the initial concept, we're not going to have the type of hardware available that can bury a habitat. And we need to find materials that have optimal shielding characteristics. And the next step after we do the carbon, I have a proposal actually it's for fiscal year that starts next Wednesday, but I haven't gotten a response yet, which is to do a kind of a hybrid or a multi-material test, introducing hafnium as a neutron blocker. Hafnium, as some of you may know, is the material that's used in the control rods for nuclear reactors. It's a superb neutron absorber, and to stop the reactions, they insert the control rods. So what we would do is we'd make a sandwich of carbon, and perhaps other materials such as polyethylene Z, which is an excellent energy absorber. And with hafnium as the last material to take out the neutrons, because the brute force approach that we've seen in all the exploration studies to date is that you just have pure mass and don't apply any intelligence or selectivity to what your material's performance characteristics are. And that's what we're trying to do in the next phase of this. It's really critical. I mean, without an effective radiation shield, we don't have a problem.
And I think Mark has mentioned the next phase. The three-phase plan that Mark himself was co-author on that I mentioned in my paper. The first is being pre-integrated, the second one being prefabricated, and then in situ is really a good idea to keep our eye on this overall picture and to consider how from the beginning, from the pre-integrated stage, what the decisions that we make for the structures that are that are pre-integrated, how will those affect how we design in situ structures 50, 60 years from now, or more? I can't really put down a timetable. Can we start with a set of semantics or a grammar that will begin with as a generator of a pre-integrated habitat, and then use that same grammar or have that influence the eventual kit of parts in phase 2, and go on into can we find native materials that will fit right into that system and keep going on throughout.
I think my question pertained to your 3 levels, because you start with the imported habitat, and of course you bury it, which hopefully Mark's going to make not happen. But if it does happen, then we've almost lost the bet, because the kit of parts approach, which would be more flexible and lead to the in situ resource utilization, would already have been made not practical by the fact that the existing infrastructure was built for an earlier time. Now, perhaps the kit of parts comes first, and then level 2 becomes level 1, and then level 1 is created. The prefab structure is created as a result.
I'm sorry I said the next phase. I should have said next year.
Well, Mark, will your shielding be thin enough to enable Scott's meter-sized panels?
Nobody can answer that question.
Yeah, yes, first we gotta see if it, first we need to see if it works. And then we need to determine how much we really need. And then, we have to figure out what Scott's panels are good for.
True.
Any other questions?
Part of my question was looking at what are the technologies we don't have that are necessary to make this whole show pull off? And one of them has to do with the materials for radiation shielding. Another one has to do with the mechanics of the in situ resource gathering, processing, and low gravity manufacturing, energy production. Is the argument nuclear versus solar? I mean, the biggest, as I understand it, obstacle is the cost to get stuff up there. It's the initial load costs that are the big deal. I mean, once you get there and can start using the resources, and that's a whole other thing that's productive in a way that pays for itself somewhat.
Yeah, so if we can start right from the beginning, and if we're talking about design grammars or whatever, we're reducing everything down to its most simple primitive. And this primitive includes manufacturing methods, very simple methods, very simple manufacturing, very simple materials, the use of the most simple materials that's possible. And then we can start right from the beginning and include not only the geometry or the interface between the pieces, but also the process for making the pieces. This has to begin right in the factory, and but once we get, we're considering all this right from the start, right from pre-integration. Then later on, when we get into in situ resource utilization, then we've already gone down to the easiest construction methods, the simplest ways. And if we could distill or process materials on the site to just plug right into that system, then I think that's the advantage of thinking of the whole picture all the way along the way.
If there are no more questions, I think we're out of time, and we all are grateful to all of you, both participants and speakers, audience.
Thank you, Alice, for organizing this session.
Let's all pat ourselves on the back.